Hi everyone, in this video we're going to go over section 4.5 examples. So first, let's work a little bit on the quotient remainder theorem. So the quotient remainder theorem says that if we have a couple numbers n and d, we can find integers q and r such that n can be represented as d times q plus r, with r is a number between 0 and d. That's the residual. So for example, if we have numbers 25 and 4, I'm essentially trying to set up 25 to be equals to 4 times some number q plus r. So pretty much what we get is how many times do we have 4 and 25? And so because we have 4 times 5 is 20, 4 times 6 is 24, so we can pretty much say, oh, okay, so this is going to be 4 times 6 will be 24, but I'm missing 1 to reach 25, so that is going to be my r. So at this point, my q is 6 and my r is 1. I should verify that this works. R is a number between 0 and 4, so it checks out and it's a good representation. Now for 50, we do the same thing. So we have 50. How many times can I fit 7 in 50? And so I'm thinking the same thing. I want to do this relationship. So 7 by 7 will be 49. So if I get 7 by 7, 49 plus 1, and then once again I get q equals 7, r equals 1. Now I have 100 and d is equals 9. So 100 being a multiple of 9. So how many times can I fit this? I can fit it 11 times. So 9 by 11 is going to be 99. And so I'm going to have plus 1 to get to 100 once again. And so the q will be 11. The r will be 1. Now, a different thing is when we have negative numbers. Remember that we can have negatives on q, but we cannot have negatives on the residual. So now we're going to see minus 15 as 4 times certain number q plus r. And so the way that we want to check this is kind of similar. We want to look for numbers so that multiply is close to minus 15. So obviously it's going to be a negative number. Now if we try, let's say 4 times minus 3, we will get minus 12, but then r will have to be minus 3, so we can reach minus 15. And one of the things is like r gotta be a positive number, gotta be bigger than 0, so I cannot use r being minus 3. So that means that minus 3 is not gonna work. Now if I use 4 though, if I use 4 times minus 4 is minus 16. So now I can add 1, and so I'm going to get to minus 15. So here the q is going to be minus 4, and once again r is 1. R is not always going to be 1. This is just something that we're getting to this point of being r equals 1, but you can have multiple examples. So now minus 7, and I'm dividing by 3. So once again, I'm trying to find q and r, so that 3 times q plus r is going to give you minus 7. So now, same thing. I'm going to use, if I use minus 2, it's too little. It's minus 6, so I will have to use a negative value, so I cannot. So I need to go further than what I usually will do. So I'll go with 3 by minus 3, and so that's going to be minus 9. So to get to minus 7, I do plus 2. And so q is minus 3, and the residual is 2. All right. So now let's compute some other values. So first, when we're doing 17 mod 5, once again, we're trying to find what is the residual. So if we're doing 17 mod 5, it's like, well, let's represent 17 in terms of 5. So 5 multiplied by q plus r, and I'm trying to figure out who r is going to be. And notice for 17, a good way to do this is, well, 5 by 3, right? So 5 by 3 will be 15. And then to get to 17, I will add 2. So this means that 17 mod 5 is going to give me the residual, which is 2. Now, 17 divided 5, and notice that here we're talking about the integer part, so we'll go with 17 is going to be divided by 5, right? And so here we get 3 plus 2, right? So the same representation. But because we're using the div, so 17 divided 5, or 17th div 5, is going to give me this value here, the 3, the q of the value. Now we do the same here for 45 mod 6. 45 can be represented in terms of 6, so 6q plus r. So I can go with 7 by 6, which is going to give me 42, right? 42, and so plus 3 is going to give me 45. Now, this will mean 45 mod 6 is 3. Minus 13 mod 5. So minus 13 represented in terms of 5q plus r. So once again, if I use but a little, like minus 2 is not going to be enough, so I'm going to use minus 3. 5 by minus 3 is going to be minus 15, but to reach minus 13, I'm going to add 2, since my residual needs to be positive. So in this case, minus 13 mod 5 is going to be the positive number 2. 100 mod 12. So 100 can be represented as 12 times q plus r. 12, how many we're going to need? We cannot have like 10. So we gotta go, do we need a 9? 9 is beyond 100, so maybe with 8. So 8 times 12 is 80, 80, and 80 by 2 is 96. So if we try 12 times 8, we get to 96, so r is going to be 4. Notice that this r is still a number that is less than 12, so we're good. And so 100 mod 12 is equals to 4. All right, so let's go with an application of this type of exercise. So it says, today is Wednesday. What day of the week will be in 50 days? And so since the days of the weeks are 7 days, so we're pretty much going to go with 50 can be divided by 7, and it's 7 more, and then plus 1. So it means that I can pretty much fit in 7 weeks later, and then going one more day. So if today is Wednesday, in 49 days, we're going to have that as Wednesday again. Okay? And so if I have one more, then this means that it's going to be Thursday. So that will be pretty much the day of the week in 50 days. Now, question number 4 is a proof. It says, prove that any 2 consecutive integers are even. And so this is probably something that I should do by cases, since it's going to be easier that way. So let r and r plus 1 be 2 consecutive numbers. So the case number 1 is r is even. So if r is even, r is equals to k for a certain k that belongs to the integers. Right? And so if r is that, then r plus 1 is just going to be 2k plus 1. And so notice that when I do the multiplication of r plus 1, we're really doing 2k times 2k plus 1. But this is just twice this. So because it's twice that, it's just going to be 2 times some integer m. And so this means that it's even. And so for the case where it's even, I have that. Now for the case 2 where we have that r is odd, then we have that r is 2k plus 1, right? But then r plus 1 is just going to be 2k plus 2. Or it's just going to be 2 times k plus 1. And so when I do r times r plus 1, which is the multiplication of those consecutive numbers, then I'm just going to get that this is twice k plus 1 times 2k plus 1. And if I just call this piece s, this is just going to be 2s, and it's going to be even. So by both of the approaches, I can show that the product of two consecutive numbers is even. Now let's go to question number 5. Says prove that n squared minus n is even. And so notice that n squared minus n is just, if I can factor this is n times n minus 1. And this is just two consecutive numbers. So this is, we have, is the product of two consecutive numbers. And so we can use the proof that we just did by number 4, n times n minus 1 is even. So this is one way of proving the results. Notice that we can always use previous results that we have used to just do solutions. Now, question number 6 says, show that for any n cube and n have the same parity. So that means that n is going to be odd or even. Okay, so this is something that we start by cases again. Once again, let n be an integer. Case 1, n even. Right, so we're going to have n even. And so if I do n cube, my manipulation here, n cube is just going to be 2k to the 3, which is going to be a cube, which I can see as twice 4k cube, or 4 times s, sorry, 2 times s. And so we have that is even. And now if case number 2, if n is 2k plus 1, that n cube is just going to be 2k plus 1 to the cube. And if I break that apart, that's going to be ak cube plus 12k squared plus 6k plus 1. This is just binomial cube, okay? Now notice that I can factor a 2 out of this piece. And this is going to be twice 4k cubed plus 6k squared plus 3k, and then plus 1. And so notice that this is just twice some number m plus 1. And so this is going to be odd, and this is odd as well. So they have the same parity. And then we just find out they have the same parity. Now, let's go to question number 7. For question number 7, we have show that any integer can be written on the form 4k, 4k plus 1, 4k plus 2, 4k plus 3 for some integer k. And so this is a consequence of the remainder theorem. So let n be an integer. So if we divide n by 4, we have 4 cases. So we're going to have that n is going to be 4k plus r, where r is going to belong to either 0, 1, 2, or 3. So the residual is that, and k is an integer, right? And this is just by the quotient remainder theorem. So we have this, and what are the options? If I plug in the residuals, then that'll be n for k, or for k plus 1, or for k plus 2, or for k plus 3. Those are all the options that we have in there. So now for problem 8, we have use the result from problem 7 to prove the square of any odd integer has the form ak plus 8k plus 1 for some integer k. If n is odd, what forms can it have from problem 7? So, from this problem 7, notice that we only have odds when it's 4k plus 1 or 4k plus 3. So there's 2 cases. Case 1, n is 4k plus 1. And so in that case, n square is just going to be 4k plus 1 square, which is going to be 16k square plus ak plus 1. And so you can see that we can factor in 8. And this is going to be 2k squared plus k plus 1. And so this is going to be a number 8, and this is an integer, m plus 1. So it has the shape that we assume. In the case 2, if n is from the 4k plus 3, we do the same thing. So n squared is just going to be 4k plus 3 squared. And it's going to be 16k squared plus 8k. Wait, never mind. 2 times 4 times 3. So 2 times 4, 8 by 3, 24. So 24k plus 9. And so from here, I can just see this as this 9. I can see it at 8 plus 1. So I'm going to factor in 8. It's going to be 2k squared plus 3k plus 1, and then plus 1. And so as you can see, this is also going to be 8 and plus 1. So both of these cases, they have the same shape. All right, see you in part 2.